So should I start?
It's up to you. I think we're ready. Thank you.
Okay. Thank you. Thank you, Kathy. So hello, everyone. Welcome to the 2024 IEEE Online Technologies. Thank you all for participating in this event. You are not speaking, and turn off your video if not presenting. For your information, copies of the presentation will not be shared. Please submit your questions and comments via the chat box. With this, I would like to introduce our speaker, Dr. Varunkumar Sivakumar. Dr. Varunkumar Sivakumar is Associate Professor in the Department of Mechanical Engineering at Indian Institute of Technology, Madras, India. He obtained his bachelor's degree in mechanical engineering from National Institute of Technology, Trichy, India, and PhD in electrical aerospace propulsion from the Indian Institute of Science, Bangalore, India. After a brief stint at IIT Ropar, he joined IIT Madras. His research group works on fundamental studies and technology development for value addition to agricultural residues and other biomass and coal. The sustains process for synthesis of activated carbon and hydrogen from biomass is a noteworthy contribution from his lab. The group is also attempting commercialization of these technologies through startups. Today, he is going to discuss on biomass, a bit of science, technology, and policy. With this, I would request Professor Varunkumar to start his presentation.
Thank you, Dr. Mitradeep. Hello, everyone. Thank you for this opportunity. I'll jump right in. I just want to set the context for the discussion here. I'm using my abstract, which you may have seen for this purpose. Interest in biomass as a cleaner alternative to fossil fuels, waxes and wanes. For instance, biomass was extensively used by the Germans during the Second World War when they were cut off from other fossil fuel supplies, and that's sort of was the resurrection of biomass as a source of energy in the 20th century. And then the interest went down, and then it comes up again when there is again an oil crisis and so on. What has remained constant in this cycle is the extensive use of some form of biomass, be it forest residue or nutshells or cow dung, as fuels for cooking and heating in developing nations. Given the magnitude of consumption of biomass and this for this purpose, improving efficiency can lead to, I'm saying, not so insignificant reduction. I'm using double negative there deliberately. Reduction in greenhouse gas emissions. This is particularly true if the alternative that is envisaged is to provide LPG or CNG to these users. The reason for this is usually the use of biomass in these contexts is very inefficient and very polluting. In this context, we'll discuss a case of development and dissemination of a clean cooking device in India. I was involved in that project as a part of my PhD work. And what I learned is, though the case of improved stoves hold the potential for global impact, interventions have been restricted to niche areas like parts of India, Africa, and other Southeast Asian countries. And the reason for me to discuss this case is to sort of highlight the challenges in using biomass at a larger scale as an alternative which can actually substitute some amount of fossil fuels. So large-scale biomass utilization for energy, fuels, and chemicals is challenging due to the distributed nature of the resource. Supply chain is a major challenge in scale-up and commercialization. I'll also discuss some work that we are doing to not so much to get into the details of the work, but I hope this will help appreciate the challenges in using biomass. And now the context is not so much of energy crisis, it's carbon emissions plus climate change combined. We have been developing processes for biomass to biochar activated carbon, hydrogen through thermochemical conversion and attempting scale up. As I said, the interest waxes and wanes. I ask myself the question, is this the right time for trying something like this? We think so, we hope so. I'll bring up questions. I'm not an expert on availability or policy, but I bring up questions that I believe are pertinent for discussion. First, we'll look at the science of biomass conversion, biomass thermochemical conversion. Biomass is everything that is forest residues, agricultural residues, cow dung, and so on. So biomass is a collective term for a diverse class of substances. Some examples here will help clarify that. Though diverse, the components of biomass include cellulose, hemicelluloses, lignin, extractives, lipids, proteins, simple sugars, starches, water, hydrocarbons, ash, or inorganics, and some other compounds. But the basic structure of all woody biomass consists mostly of three basic biopolymers: cellulose, hemicelluloses such as xylan, etc., and lignin in trunk, foliage, and bark. If we look at biomass, or different kinds of biomass from the perspective of the amount of cellulose, hemicellulose, lignin, extractives, and ash that it has, they all fall into a relatively narrow range, as you can see from this table. And in terms of the total amount of if you count the relative proportions of the atoms, carbon, hydrogen, oxygen, and nitrogen, then also we find that they all fall into a narrow range. And this is a significant point to appreciate, because in thermochemical conversion, which means subjecting biomass to heat in the presence of oxygen or in the absence of oxygen, the process displays universal characteristics because of the fact that in terms of carbon, hydrogen, oxygen, and nitrogen, in terms of cellulose, hemicellulose, lignin, etc., all biomass fall in a narrow range of these components. Just to give you an idea of the variety of processes that exist for converting biomass into interesting, useful chemicals, fuels, and so on. I don't want to go too much into the details, but what I want to highlight is it is possible, in principle, to convert biomass, be it wet herbaceous residues subjected to biochemical conversion. It can be converted into natural gas. And other dry biomass can be converted into a variety of useful products: electricity, syngas, which can be piped for cooking, syngas, which can be from which hydrogen can be separated out, and syngas, which can be upgraded into liquid fuels, including gasoline, biodiesel, ethanol, methanol, dimethyl ether, and so on. So potentially, we could get any fuel that we abundantly use today from fossil resources from biomass. And this is the primary reason, I think, why biomass still is an interesting substance to look at. So the biomass can be classified broadly into two classes: those that have large amount of water fraction in them and have it should say relatively low active biomass content, not moisture content. The first point is self-contradictory. That's wrong. It has large amount of water, and one that does not contain large amount of water. Those that have large moisture, where the active biomass content is less than 15%, are better handled by low temperature processes, mostly using microbial conversion routes. Those that have relatively small moisture, that is 30 to 50%, can be dried economically and converted to energy or fuels through thermochemical conversion routes. A large part of the biomass in the world is thermally converted to energy, fuels, and chemicals. We will focus on thermochemical conversion because that's my area of expertise. A little bit of the science of thermochemical conversion. An important question to ask is what happens when a piece of biomass is heated when we are interested in thermochemical conversion. I think this video shows clearly what happens. You will see a small wooden sphere lit using a gas lighter, and it undergoes conversion in 2 stages, flaming and glowing. Of course, somebody who has done, who has seen bonfires and other things will already know what they're going to see. But anyway, just look at this video. You see a biomass sphere lit by a gas flame. It leads to formation of a flame around the wooden sphere. The sphere transfers heat back to the surface, releasing more volatiles, and the process continues till all the volatiles are driven off. The leftover carbon reacts with the oxygen in the atmosphere and glows. And that's how the rest of the carbon is consumed. It is a rather slow process, so you're seeing this in fast forward. And the mass loss during the flaming is much faster than the mass loss during char glowing. That's what you see as a distinct difference in the slope here. This probably we could skip. Skip this. Yeah. A simple way to think of biomass thermochemical conversion is to imagine a wood sphere to be a porous carbon shell soaked in melted wax and allowed to solidify. That's the starting material. That's a model for the starting material. And upon heating this, the wax part melts and evaporates, mixes with the surrounding air, and burns in a flame, like in a candle. The flame in turn transfers heat to the sphere, which melts and evaporates. More wax part comes out as vapor and sustains the flame till the sphere runs out of wax part. After that, the leftover porous carbon glows due to air or oxygen in the air attacking its surface. Note that there is a flame surrounding the sphere. Till there is a flame surrounding the sphere, no air or oxygen can attack the carbon surface. So this is a useful picture to have in mind when we look at the technologies that I'm going to discuss. So moving on, I'm going to discuss 3 cases, technologies for biomass conversion. The case of Uja stove, the sustains process for making activated carbon and biochar, and biomass to green hydrogen. Another video.
आप जैसे रेस्टोरेंट ओनर, कैंटीन ऑपरेटर या केटरर के बिजनेस के लिए काफी मात्रा में ईंधन की जरूरत होती है और आप ईंधन के तौर पर ज्यादातर एलपीजी का इस्तेमाल करते हैं। अब तक एलपीजी के लिए सस्ता और प्रभावी दूसरा पर्याय न होने के कारण आपको हर महीने ईंधन पर बहुत सारा पैसा खर्च करना पड़ता है। क्या होगा अगर आपको एक ऐसा ईंधन मिले जिससे आपका ईंधन पे यानी एलपीजी पे होने वाला खर्च आधे से भी ज्यादा तक कम हो? सिर्फ यही नहीं, इस ईंधन के ज्वलन से धुआं न निकले, जलते वक्त आवाज न हो, एलपीजी इतना तेज हो और सुरक्षित भी हो, तो तैयार हो जाइए कुकिंग एनर्जी की दुनिया में आए हुए एक क्रांतिकारी ईंधन के लिए। फर्स्ट एनर्जी प्राइवेट लिमिटेड कंपनी का ऊर्जा जंबो स्टोव और ऊर्जा पेलेट्स रेस्टोरेंट्स, कैंटीन्स और केटरर्स के खाना पकाने के तौर तरीके में क्रांतिकारी बदलाव ला रहा है। ऊर्जा जंबो आपके हर एक एलपीजी सिलेंडर पे कम से कम 500 रुपए तक की बचत कर सकता है और ये एलपीजी इतना ही प्रभावी है। ऊर्जा जंबो एक कमर्शियल स्टोव है जो ईंधन के तौर पे ऊर्जा पेलेट्स का इस्तेमाल करता है। ऊर्जा पेलेट्स एक बायोमास ईंधन है जो एलपीजी की तुलना में बहुत ही सस्ता है। यह बायोमास ईंधन एग्रीकल्चरल वेस्ट से बनता है। ऊर्जा जंबो का इस्तेमाल बहुत ही आसान है। कंबस्शन चेंबर में पेलेट्स भरिए और थोड़े से केरोसिन की मदद से पेलेट्स जलाइए। इस दौरान फ्लेम रेगुलेटिंग नॉब स्टार्ट मोड पर रखिए। फ्लेम स्टेबल तक 3 से 4 मिनट रुकिए और आपका जंबो इस्तेमाल के लिए तैयार है। इसकी फ्लेम आपकी जरूरत के हिसाब से हाई, मीडियम या लो पर एडजस्ट की जा सकती है। इसके लिए इसमें फ्लेम रेगुलेटिंग नॉब दिया गया है। पूरी तरह भरे हुए कंबस्शन चेंबर में लो मोड 3 घंटे तक पेलेट्स चलते हैं, यानी लो मोड पर यह 3 घंटे का साइकिल टाइम देता है। नॉब हाई मोड पे लाने पर यह 3 गुना ज्यादा ऊर्जा देता है, जिसकी वजह से हाई मोड पर साइकिल टाइम 1.25 घंटे का होता है। किसी भी मोड पर साइकिल टाइम के अंत में नॉब एंड मोड पर लेने से बचे हुए पेलेट्स पूरी तरह से जलने में मदद मिलती है, जिससे 5 से 10 मिनट का एक्स्ट्रा कुकिंग टाइम मिलता है। जंबो के फ्लेम रेगुलेटिंग यूनिट में फैन, रिचार्जेबल बैटरीज और इलेक्ट्रिक कंट्रोल्स होते हैं। यह यूनिट चार्जिंग के लिए स्टोव से आसानी से अलग किया जा सकता है। पूरी तरह से चार्जिंग करने पर यह 3 घंटे के 10 कुकिंग साइकिल्स तक चलता है। जंबो की बॉडी बहुत दमदार है और 150 किलो तक का भार आसानी से उठा सकती है, यानी खाना पकाने के लिए इस्तेमाल किए जाने वाले बड़े बड़े बर्तन जंबो आसानी से उठा सकता है। जंबो में इस्तेमाल होने वाला ईंधन यानी ऊर्जा पेलेट्स अत्याधुनिक मैन्युफैक्चरिंग प्लांट में एग्रीकल्चरल वेस्ट पर विशेष प्रक्रिया करके बनाया जाता है। अब देखते हैं कि किस तरह ऊर्जा जंबो एलपीजी की तुलना में सस्ता है। एक कमर्शियल एलपीजी सिलेंडर के लिए आपको तकरीबन 1100 रुपए देने पड़ते हैं और उसमें 19.2 केजी गैस होती है। अगर आप गैस के बदले ऊर्जा जंबो इस्तेमाल करते हो तो आपको तकरीबन 50 केजी ऊर्जा पेलेट्स की जरूरत पड़ेगी, जिसकी कीमत होगी एलपीजी सिलेंडर की कीमत से आधे से भी कम। यकीन नहीं होता ना, लेकिन यह सच है। यह तो सिर्फ एक सिलेंडर के लिए हुआ। जरा सोचिए, ऊर्जा स्टोव और पेलेट्स का इस्तेमाल करके आप हर महीने, हर साल कितना पैसा बचा सकते हैं। यही नहीं, ऊर्जा पेलेट्स इस्तेमाल करके आप पर्यावरण की भी मदद कर रहे हैं, क्योंकि यह रिन्यूएबल है। तो क्या कहते हैं आप, क्या इससे बेहतर कोई ईंधन स्रोत हो सकता है? नहीं ना? तो आज ही ऊर्जा जंबो खरीदें। अब देखते हैं हमारे कुछ जाने माने ग्राहक ऊर्जा जंबो के बारे में क्या कह रहे हैं।
मेरा सिंहगढ़ रोड पे कोल्हापुरी रसा मंडल।
Yeah, I think we can skip this part. Sorry, I don't have an English version, but the takeaway message is that you could save 50% cost, and more importantly, it's replacing LPG with something that is within quotes renewable. Yeah. So the system is a very simple packed bed system. The science behind it is quite simple. There are pellets packed in a bed and in the form of a bed, and the air required for combustion, part of it goes through the bed, and the remaining part comes from the top, and that is what is creating that nice LPG-like or a gas-like flame at the top. So the science part of it is mostly about how much air should be how much air should go through the bed and how much should come from the top, and how it changes for different kinds of fuels is mostly what this is something that I did as a part of my thesis work, and it is implemented in this project. Another video, I think I'll skip this because we've seen one video of the stove. So this is how the flame looks. The idea is to have a flame that looks as close as possible to a gas flame, which users find appealing. Again, I'll skip this part. This is some optimization that was done to maximize efficiency and reduce emissions. I'll just highlight this one number, which is a water boiling efficiency of 62% in under realistic conditions. The corresponding number for a gas flame is about 65%. And the carbon monoxide emissions for this case is about 0.5 grams of carbon monoxide for every megajoule of energy delivered. And for a gas stove, this will be about 0.3. So this is in terms of performance, measured in terms of efficiency and emissions, is pretty close to a gas flame stove. Skip this. So I started working on Puja stove in 2008. The small domestic stove was already in the market at that time. It had some issues during transition from the flaming to the char mode. Resolving this problem was the starting point of my PhD thesis work. The solution, along with 2 other fundamental studies, formed the core of my thesis work. But by 2010, it was clear that the commercial kitchen market is where opportunities exist for a commercially viable operation. So scale-up was needed. I got the opportunity to work closely with First Energy in designing the air distribution system for the scaled-up stove. And then later, the company was acquired by a bigger company, and they're offering clean cooking solutions. Anyway, I'm going back in time just to give the audience a flavor of the kind of challenges that that one might face when developing technologies like this as an alternative for fossil fuel technologies. I'll move on to the sustains process for activated carbon and biochar. It is a technology that was developed at IIT Madras. It is a technology for converting biomass, particularly agricultural residues like coconut shells and other residues, to activated carbon and other fancy carbon products. Why is this important? Because activated carbon is used everywhere. It is a fantastic adsorbent. It's used in solvent recovery, water treatment, waste gas treatment, catalyst and catalyst carrier, and filters and gas mask. It is also doped. Activated carbon is contemplated as a material for carbon capture. So in this context, it assumes a lot of importance, and getting it from a renewable resource would be a fantastic way to get this precious material. And of course, it's also used extensively in cosmetics because it's a very strong adsorbent. But the current production method is very crude, very primitive. It's done in 2 steps. In step 1, a shell like coconut shell or walnut shell is converted into charcoal in pits like the one that you see on the right top. And the actual operation is very close to what is shown here. Somebody has to load the shell into the pit, light it, and control the burning behavior for 24 hours, 48 hours. There's a lot of smoke, a lot of water pollution associated with this, because once the controlled burning is over, the process is shut down by spraying water into it, and somebody has to get into the pit and take the material out. And that's how it's still happening in many parts of India. And the charcoal that is obtained from the mud pit is then activated with steam to increase the BET surface area and control the micropore, macropore distribution. There are specific processes for steam activation to control these parameters. So large activated carbon manufacturers who have the know-how for the activation process, source charcoal from different sources, and upgrade the product by activation, and then take it to the market. So around 2015, there was, because of a court intervention, this mud pit process was banned because of the pollution issues. And this issue that there is a need for an alternative process to make activated carbon and biochar from a material like coconut shell was brought to my attention by Mr. Muthukumar in 2015. At that time, he was an MTech student in our institute. And well, it says currently a PMRF PhD scholar, but he has already graduated. He's Dr. Muthukumar now. He hails from Coimbatore, a major part of the coconut belt of Tamil Nadu, and has been keen on developing and deploying technological solutions for value addition to coconut shells. So as a part of the SEMTech project, he developed a batch type reactor for activated carbon synthesis from coconut shells and demonstrated a proof of concept. This was subsequently converted to a continuous type reactor of a quarter ton a day capacity. Now we are working on putting 1 ton per day throughput system in the field. And this we have obtained the clearance from the Pollution Control Board as a cleaner alternative to the existing process. So the proof of concept batch type system is what is shown on the left. The iodine value, this is again a measure of the surface area. It could also be VET surface area. The iodine value is about 1000 milligrams per gram. The corresponding VET surface area will be about 900 meter square per gram, with a yield of about 12% was done in the batch type reactor. The continuous system, again 900 milligram per gram iodine value, meets the market requirement, and a yield of 12 to 14% was obtained. So that's about the activated carbon process. Moving on to biochar, the key innovation here turned out to be something simple. We call it the controlled oxidative flash devolatilization process. It's essentially the key strategy is preheating of the biomass, and that is the key innovation here. And preheating to about 20 to 30 degrees less than the devolatilization temperature of biomass. The devolatilization temperature is usually around 200 to 250 degrees Celsius because it's the hemicellulose and the biomass that starts decomposing at 200 to 250, and we preheat to about 170, 180 degrees Celsius. This ensures that the biomass as a bulk, there is devolatilization at the bulk level or the volumetric level and not at the surface level. And this is key for obtaining certain microstructural properties of the biochar. So the microstructure, what exactly the microstructural properties are difficult to say, but there is a very simple test that we can do to find out if it meets the criteria or not. I'll highlight that in one of the later slides. So preheating as a strategy for controlled oxidative flash devolatilization for synthesizing biochar is a key innovation here. We developed a scalable ultra-rich carbonization process in a countercurrent packed bed for synthesizing biochar charcoal with a yield of more than 33%. This is key for the process to be economically viable, and a fuel consumption rate of more than 200 grams per meter square second, which is at least 2 times more than the maximum achievable with conventional gasification. And this means that the reactors, the footprint of the reactor, etc., is smaller. The novelty of the process lies in the use of reactant preheating to slightly below the devolatilization temperature of the material as a strategy to achieve steady and controlled conversion of the material to biochar charcoal. The basis, connecting it back to the science of biomass that we saw in the first part, the basis of this idea is that the ignition time of biomass particles decreases significantly with preheating, while the time for devolatilization remains more or less the same. A specific example is we did single particle experiments and found that the ratio of devolatilization time to ignition time increases from 1.3 to 7.7 with a corresponding increase in preheating temperature from room temperature to 170 degrees Celsius. I'll show pictures of these single particle experiments in the next slide. The top row is experiment at room temperature. The ratio is 1.2. The middle row is experiment is 120 degrees Celsius. The ratio is 3.5. And the bottom row is the experiment at 170 degrees Celsius. The ratio is between 6 and 7. So there is a bit of a variation in this, but it's between 6 and 7. If you're wondering why not at a temperature greater than 170, as I told, the material starts decomposing at 200 plus degrees Celsius. So the closer we get to 200, the material will start decomposing even before the process starts. And that's not the aim there. We want to keep the material at a temperature where it will not start decomposing till it reaches the reaction zone. Comparing the performance with a conventional process, the yield we get for these three biomasses in the range of 23 to 27%, while in the conventional process, you will get less than 20%. And at a fuel conversion rate that is 4-5 times higher than the conventional process, therefore smaller reactors and more decentralized production. And that's key here because aggregating biomass, there are supply chain issues. And the key properties of the biochar is it should have PET surface area of less than 50, preferably. Otherwise, it's very low, 3.3. The pore volume should be less than 0.05 cc per gram. And I was referring to the microstructure in one of the earlier slides. A very characteristic feature of the right microstructure is when you drop the biochar, it should make a metallic sound, as if a piece of metal or glass is dropped on the floor. And only when we do preheating, the product makes a metallic sound when dropped on the ground. Otherwise, it doesn't. It sounds very similar to, otherwise, it just sounds like firewood falling on the floor, non-metallic sound. These are the Muthukumar and Mr. Syed, the students who worked on this project. What you see in the picture is a system that we have in the lab as a proof of concept. They are the winners of the Carbon Zero Challenge 2019, and the activated carbon process and the biochar process are both patented. I'll just quickly touch upon this so that we'll have some time for discussion. Biomass to hydrogen, something that we are working on right now. Background is a series of laboratory studies were conducted on packed bed biomass reactors at IIT Madras between 2014 and 2020. A wide range of operating conditions with mixtures of oxygen, carbon dioxide, steam, and about half a dozen candidate biomass, including a few types of agricultural residue-based pellets and coconut shells were covered in these studies. Several unknown crucial fundamental results were uncovered and published, several articles and conferences. The key takeaway was we were interested in the factors that are critical for scale-up and transformation of the lab-scale system into a technology package for field deployment. The net carbon dioxide and steam conversions have been accurately quantified to enable scale-up and automation. The energy input in terms of the energy contained in the biomass and auxiliary processes, if we look at in the basis of grams of hydrogen produced for every megajoule of energy that is consumed, is about 0.21 megajoules per gram. This is about 30% lower than the contemporary gasification-based technologies. And it's also lower than electrolysis, but that's not a, I think it's not a fair comparison. Other factors have to be taken into account. Tar-free exit gas without any need for downstream treatment, and therefore simple and economical post-processing at industrial scale. We always look at this because this becomes a challenge when we try to scale up. Use of low temperature steam. Other processes require at least 750 degrees Celsius. Our process can work with 200 degrees Celsius steam. And therefore, the associated simplicity in steam generation equipment scale up. And it can handle a variety of fuels. Still, there are restrictions, not all fuels, but many fuels. Fuels like this. 4 types of biomass pellets is what we are currently working on, but fuels of this type are ideally suited for this process. So the current state of this is we have a demonstration system in the lab working at, again, 1/4 ton per day, and we are working on setting up a 1 ton per day in collaboration with an external partner. And there could potentially be a startup in this area also. We are exploring that possibility. Very quick look at policy matters, and I'm just going to bring up questions because I'm not an expert. When it comes to biomass, there's always a question of availability. I believe when seen at the country level, we get numbers like 500 million metric tons annually, and or maybe more. And some calculations show that if all of that is converted into some form of liquid fuel, it could substitute 10% of what India imports, 10% of the crude that India imports, and so on. There are several scenarios that show very promising numbers. But the key challenge is that not all of this is available at the same place. Setting up supply chain is very challenging, but looks like things are getting better. Of course, many of you may also be aware of the issues of burning of the fields, leading to severe deterioration in air quality in the Indian capital during winters. So this is a multi-dimensional problem, and solutions solutions are important, not just from the perspective of substituting fossil fuels and climate change, but also from air quality point of view. There's this question of whether this is, I said at some point that renewable within quotes. So the question of carbon neutrality is always there. For a long time, I still believe it is true even now that the European Union has somewhat looser rules for classifying what is renewable in terms of biomass and so on. But at some point, there was a lot of discussion on whether these rules must be made tighter. And I think nothing has changed, but there's a lot of push to not classify biomass on this as equivalent, let's say, to power produced from solar panel or wind. Okay, so at least till some time ago, it was on the same footing as wind and solar. And probably there are experts here who can correct me if I'm wrong, but that's my understanding. But if you look at the National Green Hydrogen Mission of India, it classifies hydrogen from biomass as a cheap source of green hydrogen. So by saying green hydrogen, we obviously mean it has no carbon footprint, but that is again debatable. So this is a somewhat gray area. But I think when it comes to technology scaling and technology deployment, these questions are important, but not a deciding factor, because at least in India, that there is an issue of handling agricultural residues, and therefore technologies that can handle agricultural residues are welcome and have a market. The other question, of course, is should we start growing energy crops? Again, I'm sure there are experts in this forum who, of course, know a lot more than me. But again, this leads to the question of food versus fuel debate, and which land is suitable for energy crops. Can it be repurposed for growing food crops and so on? And again, it's a gray area, at least for me. I'd like to summarize. So biomass conversion as a scientific problem will continue to be explored. New questions keep popping up. Advanced thermal, biological, and even electrochemical methods are under laboratory investigations. Development of technological solutions to address niche problems like cooking, heating, synthesis of activated carbon, biochar, hydrogen for specific applications. For example, for use in a steel plant. It's local, hydrogen is generated there and used captively in the steel plant. Will continue to make an impact at local economy level, maybe even in a fertilizer plant for making ammonia. But when it comes to question of large scale production, let's say large scale production of liquid fuels and distributing it through fuel stations, as I said, there are scenarios that indicate a potential solution, a potential substitution of up to 10% is possible in principle. In reality, only time will tell. Again, interest has gone up and come down several times in the past. And that is why I believe it is important to have a holistic view of the energy problem, a bit of science, technology, and policy. Thank you very much. I'll be happy to answer questions.
Thank you, Professor S. Varunkumar, for this wonderful presentation. So just to remind, participants can put their questions on the chat box and I can then take them up from there. So we have one question from Dayalan. It's how feasible is it to combine your biomass combustion technology, which is the stove, with the localized carbon capture and storage?
That's a very interesting question. And hello, Dayalan. I should have said hello to him. We've known each other for a long time. I don't think right now there is any carbon capture technology that can work at that scale. And even when such a technology becomes available and let's say it's cost competitive, yes, that is something that that can be tried. But the idea is that the biomass that you burn grows again by fixing the carbon dioxide that it emits by burning. And that's the logic that is used for arguing that biomass is carbon neutral. So the carbon capture system from that point of view is already there. So if you grow the crop again, it fixes carbon dioxide from the atmosphere, and therefore it's carbon neutral. So that's the argument right now. Yeah.
All right.
I hope that answered.
So yeah, I hope so. So
Yeah.
if before we get back to this question, just in case if there is any, I have a very, I'm just curious to know, you have mentioned that there is a process that you are currently exploring from biomass to hydrogen process. Now, once we do that, is there any technology that are associated in storing that hydrogen, or is there any safety issues in this regard? Just curious if there is anything of that sort that may also come into the picture.
Yes, if it's done at large scale, then the question of storage and materials for storage and safety are most important. But right now, our focus is on deploying this technology in places where hydrogen can be used right away. So in a sense, we are avoiding the difficult problems by not storing it. For example, in a steel plant, where hydrogen is a very appropriate fuel because it gives heat and also reduces the iron ore to iron. So you generate the hydrogen and use it right there. Or in a fertilizer industry, you generate hydrogen and immediately convert it into ammonia, and which immediately becomes urea. And therefore, the question of storage is avoided. That's not a solution, but we're just avoiding the problem.
I see.
But it is critical when we are looking at large scale generation. Yes.
Yes. So is this technology something that is coming up, or it's already there, this biomass to hydrogen process that you are discussing?
So we are trying to commercialize what we consider as a better, improved version of several processes that exist already. So this is not new in the sense that, of course, people have obtained hydrogen from biomass in the past, but there are several issues when it comes to scaling up the process, and we believe we have a process that is more suitable for scale up.
I see.
So the low temperature, the low steam temperature, the tar-free exit gas, and 30% lower energy input are something that we believe are the USP of the process, which will enable it to become bigger and have an impact at scale.
Okay. Okay, I see. So again, in this line, so how much of the biomass products are currently available in the market? If I look at the market, and then if you can give me some sort of idea, that would be really interesting.
You mean the fuel for this
Yeah,
process?
in the fuel sector, yes.
Okay, again, I don't think I can give you a very quantitative answer here. We have started, so we are planning to set up a 1 ton per day plant in a place that is about 30 kilometers from Chennai. So we have started exploring the availability in a 50-kilometer radius from that location. And from the data that we have so far, we see that we could run a plant of 10 tons per day capacity at this location throughout the year, or 95% of the year, without any difficulty. So what we see is a lot of decentralized biomass pre-processing industries that have sort of sprouted in and around this place. What they do is they source loose biomass from, or a variety of biomass from wherever it is available. They process it, convert it into a standard fuel like a pellet or a briquette, like what you see in these pictures. So these are just biomass that are compacted into pellets and briquettes, and they sell it and they do this at scale and sell. So we're trying to set up a 1 ton per day plant, but we see that if we scale up to 10 tons per day, and we have, let's say, 3 or 4 plants within the 50-kilometer radius, we'll be able to run the plant for about 95% of the time in a year. So that's very promising. That was not the case, let's say, 10 years ago.
Okay, I see. But is there any?
I have information only in this geography. I do not know what it is at other places. Yeah.
I see. But is there any other alternative to this? I mean, whatever you are developing is currently also available in the market, in the commercial area, I'm saying.
Do you mean the process, or
not the process, maybe the product? I mean, is there anything commercially available which is similar to this, also an biomass product
biomass? Sorry, please finish your question.
Yeah. No, I'm just asking that if there is any similar products that are already available in the market in the fuel sector that is coming up or that is coming out of biomass process or something.
Not to my knowledge, not at least at any meaningful scale, where
I see.
let's say meaningful scale, let's say relative to the amount of carbon dioxide avoided relative to the total that we emit and so on. I don't think anything is happening at a meaningful scale from that perspective.
I see. So we got another question, which is, what are the main obstacles to commercializing this technology as a consumer product?
Okay, as a consumer product is, I am going to interpret that as selling pellets directly to customers.
Yeah, something similar.
Varun, are there any barriers for acceptance of the product in the consumers as a stove, or to use this as a regular life?
No, there's definitely a lot of barriers, and that's one reason why the push is not in selling domestic stoves anymore. That transition happened in the previous decade itself, when it became clear that what people prefer is an LPG stove. in terms of convenience, and even though it is expensive, again, now there are schemes in the country where LPG is almost free. So the push is not in the small domestic stove domain anymore. It's only at the competition is only with commercial LPG, which is about 3 times more expensive than domestic LPG. And we have even moved away from that and looking at installations of biomass to hydrogen process of scales like 1 ton per day, 10 ton per day, maybe even 50 tons per day in the future, where all the hydrogen will be captively used by an industry. So there's no, it is a B2B model and not a B2C model anymore, because it is only at that scale where we think the economics it makes sense.
Thank you.
So is there any other questions from the audience? So I have another very small query that is related to the policy, because you mentioned the policy part at the later part of your presentation. So how do you see that, how these policies are changing as far as the biomass to energy conversion is concerned over the past maybe few years or a decade?
The policies have only become more encouraging for us to continue to develop technologies and try to scale this up. So yeah, I think that's, I want to stop there, because if you go into details, then it becomes a debate on we're then nitpicking. So what is good and what is bad.
But that is good to know
policies
that
are generally
the
becoming
policies are
encouraging.
encouraging this type of products. And now when you say that the policies are encouraging and they are really helping this type of work to flourish, having said that, I think already there is a question that how do you see that the acceptance versus the policy? Because you also have said there is some certain sort of barrier when you come up with such products, when you compare it with traditional, say, LPG or something. So how both of these are going hand by hand?
So the policies are encouraging, definitely, but the shift is, as I said, in models that are business to business and not business to customers. So targeting, let's say, so the small domestic stove is a novelty now, and not it's not an essential, or it's not a necessity anymore in many parts. There's still parts where there are still several locations where biomass is used, LPG availability is poor, but even there, what people desire is LPG, irrespective of how close the biomass stove comes to being like LPG. What they desire is still LPG, and that's the reason why it looks like it's better to make hydrogen, large quantities of hydrogen, and sell it to a business like a steel plant or a fertilizer plant or an aluminum smelting plant and so on. Or even consider blending it with natural gas in pipelines up to 5%.
Nice. Okay. So if there are no more queries from the audience, I would like to thank the speaker, and that's a wonderful presentation, Professor S. Varunkumar. With this, I think today's session is over.